Okay, so this time I'm going to talk about two-dimensional projectivities. So there's really two main types of these things, which are well focused on, and those are collineations and correlations. These are terms introduced by Mobius in the 1800s. And let's start by talking about collineations. So a collineation is a mapping which sends points to points, and it sends lines to lines, and it acts as a bijection upon the points, and it acts as a bijection upon the lines. So a bijection is a one-to-one onto mapping. So in other words, every point is associated with another point, no two points are sent to the same point, and every point is sent, every point has another point which is sent to it. Okay, so we have this bijection. It works as a bijection on the points, it works as a bijection on the lines, and it preserves incidence. So that means it has to transform every range of points on a line onto another range, and it has to transform every pencil onto another pencil, and quadrangles into quadrangles, and so forth. And that's the definition of a collineation. So a collineation, just to summarize, is a incidence preserving mapping that sends points to points as a bijection and lines to lines as a bijection. Okay, so since this is projective geometry, we're going to be especially interested in what are called projective collineations. So that's technically a collineation which transforms each one-dimensional form. When I say a one-dimensional form, I mean a range of points on a line, or dually a pencil of points, a pencil of lines for a point. So it transforms each one-dimensional form projectively. So, in other words, say we've got some line B, and we've got some point Y on it. Well, if our collineation is a projective collineation and it sends this line B to another line B dash. So let's say this variable point Y is getting sent to some point Y dash on B dash. Well, in that case, there has to be this projectivity existent that sends Y to Y dash. So in other words, whenever we transform one-dimensional form to another, there has to be a projectivity that also does that same action. Now, technically in our definition, we're going to require that holds for every range, and every pencil. But an interesting fact, which is a little bit similar to something we encountered in discussing involutions, is that actually if this kind of property holds for a single range, then it has to hold everywhere. So in particular, we have that any collineation that transforms one range projectively, in other words, it has this property that there's a projection that mirrors its actions. Well, if it transforms one range projectively, it has to actually be a projective lineation. It has to transform every range and every pencil projectively. So how are we going to prove this result? Well, let's suppose that A and A dash are a pair of lines whose ranges get transformed projectively by our given collineation. So now we want to show that this collineation actually transforms every pair of ranges projectively. So let's have a look at another line, let's say B, and let's suppose that that gets put in correspondence with a line B dash, and we're going to let y be a variable point on B, and we'll let y dash be the image of y under our collineation. Now, in addition, just for the sake of construction, let's take another point O. We'll suppose that O is a point which is not on A and it's not on B. Now, this line OY is going to intersect our line A, the one that gets projectively transformed. It's going to intersect that line somewhere. So let's say it intersects it at a point X. So it follows then that the corresponding line, O dash Y dash, has to intersect this line A dash at some point X dash. So O dash Y dash has to intersect A dash at X dash. And now what we can do as desired is to find a projectivity. We can do a perspectivity from our point Y to point X. That's actually an elementary correspondence that we can do. So given our generic point Y on our generic line B, what we can do is, since we have this point O, and we know that this line through O links Y to X, well, we can then do a perspective to get from Y to X, just using centre of perspective O. And then, well, we know that X is a point on this line A, which we know is projectively related to this line B, this line A dash, by this projectivity that sends X to X dash. So we have that X, there's a projectivity from Y to X, there's a projectivity from X to X dash, and then using centre of perspectivity O dash gets us a perspectivity from X dash to Y, and stringing that all together, from X dash to Y dash, and stringing that all that together, we have a perspectivity from Y to Y dash, which is exactly what we want. So we've shown that for a generic line, we can have this projectivity, which, we have this projectivity which transforms it projectively. And that's just an implication of the fact we have a projective collineation and that it works on a single line A. We have a collineation and it works projectively on a line A. So that's the end of the argument. We could have gone through it again, used the kind of dual argument to establish the kind of dual result that if we transform a pencil projectively, then we transform all pencils projectively. So we're going to see this duality help us out a lot in the discussion today. So, okay, let's move on to another result then. So, one of the most powerful ideas we've been using so far for one-dimensional projectivities is this idea that if you're going to, let's say, hold 3 or more points on a line fixed when you're transforming a range projectively, then you have to actually have the identity. The fact that there are 3 invariant points implies all members of the range are invariant. So that's a kind of 1D invariance theorem or something. And here's the 2D analog of it. What it basically says is that if we have a projective collineation that is going to either leave 4 lines of a quadrilateral or 4 points of a quadrangle invariant, then in fact that mapping has to be the identity There's no other projective collineation which does that action. Okay, so we want to show then that, let's just do this argument for a quadrilateral, because duality will suffice to fill in the blanks for the quadrangle. So we want to show then that if a projective collineation leaves 4 lines invariant, the 4 lines of a quadrilateral, the initial 4 lines, or the sides or edges if you like, well, if it leaves those invariant, then it has to leave every point and every line invariant. This is the claim. So how do we show it? Well, we've got these 4 lines which are invariant. Now, looking at where those lines intersect each other, that gives us 6 points. Since each of those points lies on one of these lines, it too has to be invariant under our projective collineation, in the sense that it gets mapped around back to itself. Now, if you look at any one of those lines, one of those sides, that actually has to hold 3 of these points. And so, since it holds 3 invariant points, it's a consequence of axiom 6, one of our fundamental axioms discussed in the 3rd lecture, that given that this projection from the range has 3 invariant points, it has to have every point invariant. It has to work as the identity on each of these lines. But there's more than that, because if we consider any other line, well, that other line has got to intersect with each of these 4 lines of our initial quadrangle. So there's got to be 4 points on this new given line, 1 point for each line of the initial quadrangle, and each of those 4 points has to be invariant. So in fact that implies that this projectivity works to leave that generic line invariant as well, so a consequence of our axiom. So this essentially shows that our projectivity leaves every single line invariant, and we can do a dual argument with respect to so that was for quadrilaterals, which are constructed by using 4 lines. But we could have done a dual argument for quadrangles. Okay, so this is obviously quite a useful result, because we see that these quadrangles and quadrilaterals are helping us to determine whether or not given projective collineation is the identity. But actually the concept's even more powerful than that. The interrelationships with these forms is more powerful than that because of this next result, which actually says that if we're given let's say we're given 2 complete quadrilaterals, or quadrangles, but I'll discuss it with respect to quadrilaterals, and it should be fairly obvious how to dualize this result and its proof. So let's say we're given 2 complete quadrilaterals, and let's say that the sides of those are labelled in some way, in some corresponding way. So, for example, we might have a side E on our first quadrilateral. That would be corresponding with the side E' on our second quadrilateral. Well, given this, what our result is claiming is that there's actually going to only be one projective collineation which does that kind of transformation. So, in a way, this is a sort of 2-dimensional analogue of the fundamental theorem of projective geometry, in that it infers that given the information of how a projective collineation transforms one quadrilateral into another, that's enough to uniquely specify how this projective collineation works on every single point and every single line. So, okay, what's the proof then? Well, let's suppose that we've got a quadrilateral which has these 6 vertices. So it has four lines, 4 sides, and 6 vertices, which we shall call D, E, F, P, Q, and R. So they're the vertices of the first quadrilateral. The second quadrilateral's vertices are correspondingly labelled D dash, E dash, F dash, P dash, Q dash, R dash. So what we're going to do, we'll suppose that we have, so the first thing we want to do then is to show that given these two structures, that there is actually a projective collineation which puts these in the proper correspondence. So how can we do it? Well, let's just suppose that we have an arbitrary line A. So that line A is going to obviously meet our quadrilateral in a couple of points, which we shall call X and Y. And well, without loss of generality, we can suppose that point X is a point on the line DE, and point Y is a point on the line DQ. So if you have a look at these two lines, let's start with this line DE. Well, that has 3 vertices, okay? It has these vertices D, E, and F. And the corresponding vertices of the corresponding quadrilateral are going to be D dash, E dash, and F dash. So we have 3 points in our initial structure, 3 collinear points, and 3 collinear points in our final structure. Well, we can find a projection then from one to the other. So we can find this projection from D, E, F to D dash, E dash, F dash. And similarly, we can find a projection from D, Q, R to D dash, Q dash, R dash. So what we can do then is we can use this information to determine this line A dash, which goes from the image X dash of X to the image Y dash of Y. Well, sorry, it's a line that goes through those 2 points. So how do we do that? Well, we've got this variable point X, which is on this line DE. So given the projectivity I was just talking about, that sends DEF to D dash, E dash, F dash, well, let's look at how that projectivity also works on this variable point X. So it's going to be a projectivity from DEFX to D dash, E dash, F dash, X dash. Similarly, there's going to be this projectivity from DQRY to D dash, Q dash, R dash, Y dash. So we have that this mapping works on these points like so. So how are we going to prove that it's a projective collineation? Well, we want to show that it preserves incidence, okay? So in particular then, we have this point X on this line DE. So let's suppose that this line A, which links X and Y, actually works as a pencil, okay? So it's a pencil through some point that links this variable point X on DE with this point Y on DQ, okay? So what that means then is that there has to be a perspectivity via this line, of course, which sends X to Y. So if we string together then what we know about the existence of these projectivities as well, we have that there's a projectivity from X dash to X, there's a perspectivity from X to Y, and there's a projectivity from Y to X dash. So the upshot of this is, well, there's a projectivity then from Y dash to X dash. But there's actually more to it than that. You see, if we have a look at that perspectivity from X to Y, well, since this point D then that's a perspectivity essentially from the line DE to the line DQ. And so D's obviously got to be a invariant point of that perspectivity. But the thing is, it follows that this image then, d dash, has to be an invariant point of this projectivity from x dash to y dash, which we've just constructed. Now, if you remember one of the corollaries from the fundamental theorem of projective geometry, that was that if we have a projectivity that sends one range to another, and that projectivity leaves the intersection point of those two ranges invariant, well, it has to be a perspectivity. So this actually gives us this mapping from which sends x dash to y dash, this projectivity has to actually be a perspectivity. In other words, just as we can think of this line A is varying like a pencil, we can also think of this line A dash joining x dash and y dash as varying like a pencil. In other words, our projectivity is going to be sending congruent lines to congruent lines. So this means that this transformation has to be a line-to-line and a point-to-point transformation that preserves incidence. So that shows that this projectivity sending x to x dash has to be, in fact, a projective collineation. So what we've done so far then is show that given if one exhibits these corresponding quadrilaterals, there is a projective collineation which does the job we want, but now we have to show its uniqueness. So to do that, let's suppose that there was some other projective collineation transforming d, e, f, p, q, r into d dash, u dash, f dash, p dash, q dash, r dash. But now let's suppose that projective collineation, this new one, is going to send line A to another line, not A dash necessarily, but another line which we'll call A1. So now we can use this supposition to imply, well, you'll see. So the thing is, since we have this new projective collineation, we can do its inverse. Now the original sends A to A1, so the inverse, which is called row inverse, sends A1 to A. Now the thing is that since the thing is now that this inverse mapping is obviously going to send d dash, e dash, f dash, p dash, q dash, r dash to d, e, f, p, q, r. And if we then compose that with our initial mapping, well, that's going to send d, e, f, p, q, r back to d dash, e dash, f dash, q dash, r dash, which I shall just call the dash structure, just for the sake of brevity. So composing the inverse of this new projection with our original projection gives us a projection from this dash structure onto itself. But the thing is now, this resulting projective collineation, which we get from composing row inverse with our original, well, that's just going to be a collineation which preserves this quadrilateral with vertices d dash, e dash, f dash, p dash, and q dash. And then it follows from our last result that the fact that that does leave the quadrilateral invariance means that it has to actually be the identity. So what that shows then is that this mapping row inverse actually has to be just the same as our original mapping. Sorry, this means that this mapping row has to actually just be the same as our original mapping. In other words, it has to be unique, and this line A1 has to actually just be the same as this line A dash. So this shows the uniqueness of the results. So, of course, all of this argument can be repeated if one considers quadrangles instead of quadrilaterals, and basically then one could just dualize the arguments to get the other side of it, and that's probably quite a worthwhile exercise to do, to really see how all this stuff works in a dual kind of way.
Okay then, so now it's time to talk about a special kind of projective collineation, which is called a perspective collineation. So this is quite closely related to Desargues' theorem, because essentially what a perspective collineation is something which preserves both the axis and the centre of perspectivity related to two perspective triangles, but we're going to introduce it in a different way now. So let's suppose that we have a couple of complete quadrangles. One is on vertices P, Q, E and D, or I suppose I should say D, E, P and Q in alphabetical order, and the other quadrangle is on D, E, P dash and Q dash. Now, according to our previous result, there's going to be a unique projective collineation that sends this first quadrangle onto this second quadrangle. There's just going to be one projective collineation that does that, and moreover, this line, which is a common line to both quadrangles, DE, let's label this line little o, and it's clear then that this projective collineation has to leave that line O invariant, because it's the only collineation that sends one quadrangle to the other, and so it has to keep that common line of those two quadrangles the same. Well, okay then. Now it follows that actually, if you think about it, this has to preserve every single point on that line. There's this projective collineation. But we can actually go further. Okay, so we're also going to have that these two lines, the one that goes through P and P dash, and the one that goes through Q and Q dash, those also have to be invariant under this projective collineation. And so does the point where they intersect, which we shall call capital O. Now what we can do is we can define point R to be the point where the lines DQ and PE meet, and similarly we'll define R dash to be the point where DQ dash and EP dash meet. So we get these sort of third points of our triangles. And now it should be clear that these two vertices, R and R dash, they've also got to be corresponding to one another under this projective collineation. And again, that line through R and R dash also has to go through O. And so by a kind of dual of our axiom 6, we have that every single line passing through O has to be invariant under this collineation. That's big O. So now we find this relationship where basically we have these two triangles, P, Q and R, and P dash, Q dash and R dash, which are perspective from point O, or centre O if you like, and also perspective through line little o, or axis little o if you like. So basically we have this setup which is rather similar to Desargues' theorem, although we arrived at it through a different kind of construction. Now there are two different possibilities. This generic case where this centre of perspectivity big O doesn't lie upon the axis little o, that's called a homology. Those are the more general kind of thing, which was studied by Poncelet. But also Sophia Sly studied special kinds of perspective collineations, which are called elations. And in an elation, the centre big O of perspectivity actually lies upon the axis little o, like this. Okay, so how do we actually figure out what the image of a point, let's say R, is under a given homology? Well, it turns out that all we need to know is the centre of the homology, capital O, that's this yellow point here, the axis of the homology, little o, that's this yellow line, and one pair of corresponding points, P and P dash, that lie upon a line which goes through the centre. So given all this information, we can determine what happens to this point R. So in particular then, what we want to do is find the image R' of a generic point R. So how do we do it? Well, firstly, the degenerate cases, obviously if R touches O, if R touches the axis or if R touches the centre, then it's going to be invariant. So in those cases it's trivial because R' is equal to R. So let's suppose that's not the case. And also, just for now, let's suppose that R doesn't belong to this line OP. So it's a kind of randomly chosen point. How do we find R' in this case? Well, firstly, let's find this point E by drawing a line through P and R and finding out where that meets the axis O. So here's point E. We find it by intersecting the green and yellow lines. And now, fairly simply, we just have that R' is going to be equal to the place where a line through this new point E and our other image point P' meets the line through O and R. So intersecting those two, we find that R' equals EP' intersected with OR. So that's the general case, how to determine the image of a point R. But there's one other case we ought to consider, which is what happens when R is actually part of this line belonging to OP. So in that special case, what we can do, we can pick another point Q, which is outside O and outside of O and P, just like R was in the previous case. So we have this point Q, which we just randomly put anywhere, and we can determine its image via the previous argument, which is Q'. And in that case, if we just let D be the place where this line QR meets the axis O, little o, well, in that case, we're going to have that the image R' is just going to be equal to the place where the line through D and Q' meets with the line O and P. So this gives us a way to figure out what the image is of any given homology. Recall that a homology is one of these perspective collineations within which the centre big O does not lie upon the axis little o. So in this special case where the centre big O is on the axis little o, we have an elation, and in that case we really require less information to determine how this elation works. In particular, all you need to know is what the axis little o is and a pair of points, say, that correspond to each other, say P that corresponds to P', because in this case you can determine the centre of perspectivity O to be the place where this line through P and P' meets the axis little o. And after you've done that, you can basically use the reasoning given in the previous argument about homologies to work out what the image of a generic point R is. And because this case is so nice, we can use this little notation to denote how an elation works. So O semicolon P goes to P dash, that's a notation for elation when it's in square brackets, and it notationally contains all the info that we need. Okay then, so here's a really important result which has lots of implications, which says that any collineation at all is actually going to be a perspective collineation when exactly one range of its invariant points is perspective. So the proof then? Well, firstly, let's suppose that one range of this collineation is perspective. Sorry, is invariant. Well, in that case, I mean, the identity mapping, which leaves all the points invariant, that is a projectivity. So that implies that we have a projective collineation. But is it a perspective collineation? Well, yes it is, as we shall soon see. The thing is, the crucial observation is that outside of this range of invariant points, which we can call little o, there can't be any other points, or there can't be more than one other point which are invariant. Why? Well, because if there was two such points, then what we could do would be to draw a line through those two such points, and we could then choose 2 points on little o. Sorry, let's say there was two other points outside of this line O which are invariant. Let's call them x and y. Well, in that case, we'll pick a couple of points, say x dash and y dash on line O, and together x, y and x dash y dash would form a quadrangle, which would be invariant under this projective collineation. So by our result, that if such a thing leaves a quadrangle invariant, it is the identity, that implies that our projective collineation would be the identity. Here the period of a mapping is the number of times you need to apply it to return the system configuration back to itself, given that you're applying the mapping at least once. So also we have the converse result holds. It turns out that every single projective collineation of period 2 is in fact a harmonic homology. So I'm not going to prove this here. I'll leave it as a somewhat challenging exercise for adventurous viewers to try and find a proof to this result. But our mapping clearly is not the identity, since it only leaves one range of points invariant. Okay, so we know that there can't be more than 1 point outside of line little o which are invariant. So let's just consider the case where we have 1 point, big O, outside little o, which is invariant. Well, if we consider any line through that point, big O, that line is going to be invariant where it crosses through big O, and it's also going to be invariant where it intersects with the line little o. So it follows that that line itself has to be invariant, not full of invariant points, but the line has to get mapped to itself under this projective collineation. And so what that actually means is that we have a homology. Now, the other case is, of course, when this point capital O actually lies upon the line little o. In other words, if every invariant point belongs to little o. And in that case, we just have an elation. So, there's a few important implications of this result. One of them is that every single collineation that has a range of invariant points also has a pencil of invariant lines, notably all the lines that go through this centre of perspectivity. Sorry, this centre O. Also, if we have an elation, then that's the case where this only invariant point big O, which is not necessarily upon the line, actually is upon the line. And in that case, we have an elation. All the invariant points are on the axis little o. The other case is, of course, the probably more common one, where this centre big O is going to be the only invariant point which is not upon the axis little o. So that's the case for homologies. Okay then, so now let's talk about some special kinds of homologies. So in general, a homology is just going to be determined by giving its centre, big O, its axis little o, a point P, and the point P dash that it corresponds to. However, there's actually a kind of simpler class of homologies, which are called harmonic homologies. And those have the property that the harmonic conjugate of the centre, O, with respect to a couple of corresponding points, P and P dash, always belongs to the axis little o. So for these special kind of homologies, there's actually we actually need less information to specify them. So in particular, all we need to know of such a thing is its centre and its axis. Why? Well, let's say we want to find out what the image of a point P is. Well, the corresponding point P dash is just going to be then the harmonic conjugate of P with respect to both the centre and the place where this line OP meets the axis little o. And for this reason then, such a mapping clearly has to have a period of 2. Okay, so finally then, let's talk about correlations. So, a correlation, unlike the collineations we were discussing before, actually sends points to lines and lines to points. Now, it does that as a bijection. So, and it preserves incidence. So in a way, it's quite similar to a collineation. The difference is that whereas a collineation sends each point to a point and each line to a line, a correlation sends each point to a line and each line to a point. So it has this interesting property of kind of changing one form into the opposite, or the dual. So then, such a projective correlation such a correlation is going to preserve incidence. So that means it'll have to change ranges into pencils, pencils into ranges, quadrangles into quadrilaterals, quadrilaterals into quadrangles, etc. And so it's clearly going to be a dual kind of concept. The dual of a correlation is a correlation. The inverse of a correlation is a correlation. Also, note that the product of two correlations, that's the thing you get if you do one correlation after another, is going to be a collineation. And we're going to call such a correlation projective if it works as a projection on every single one-dimensional form. That is, on every range or every pencil. So for example, if a projective correlation works upon a range of points on a line A, and X is a point on the line A, and X gets sent to some line E, well then there has to be a projectivity that sends X to E, where X is a variable point and E is the variable edge it gets mapped to. So we have to have this property that it works projectively on every single one-dimensional form if it's a projective correlation. Now, we actually have the kind of foundational results about projective correlations are pretty much analogous to those we found out for projective collineations. Excuse me. So let me just say that again. The foundational results for projective correlations are analogous to those for projective collineations. In particular, we have this kind of if a property holds somewhere it holds everywhere kind of feature. So in particular, if we have a correlation that transforms any single range projectively, then it has to be a projective correlation which transforms every single range and every single pencil projectively. So we saw an analogue of that. I'm not going to give the proofs to these because we don't focus too much on correlations in future lectures, but the proofs are somewhat analogous to the ones given before. So the other main result then is that a projective collineation is really fundamentally determined just by the way that it sends the vertices of a quadrangle to the sides of a quadrilateral, which are correspondingly named. So I mean, we could name the vertices of our quadrangle capital A, capital B, capital C, capital D, and the sides of our little quadrangle lowercase a, b, c, d. And then given that we have a mapping, given that we have given that we have a correspondence that sends big A to little a, big B to little b, etc. Well, there's only going to be one projective correlation that does that kind of mapping, and there's going to be exactly one. So this is a kind of analogue of the, well, given how it sends a quadrangle to a quadrangle, it's uniquely determined kind of property, which projective collineations have. And this basically gives the analogous result that given how it sends quadrangles to quadrilaterals, that's enough info excuse me, I've spelt this wrong. I ought to have put quadrilateral here. There we go. Yes, we want to be sending a quadrangle to a quadrilateral, of course. And given how that's achieved, while respecting the labels of things, that's enough information to uniquely determine a given projective correlation. So such a thing always exists, and the info uniquely determines it.